Okay, let's unpack this. When you look up at the night sky, I mean, it's just vast, isn't it? You can't help but wonder if we're alone.
It's the big question.
Mm-hmm.
And the search for other worlds, especially ones that might, have life.
It's one of humanity's biggest quests, really. And lately, wow, the discoveries are just rolling in.
It's incredible. The field moves so fast. Each new planet isn't just another point on a map. It makes us rethink, well, everything. Where life could be, how it could be.
Absolutely. And that brings us perfectly to today's deep dive. We've got sources here on two really fascinating exoplanets, Kepler-725c and K2-18b.
Two very interesting cases.
Yeah, and our mission basically is to go through this material, understand what makes them tick, how we found them, what we actually know.
And maybe what we don't know yet.
Exactly, and why they matter, because they represent sort of different but equally vital approaches in the hunt for habitable worlds.
You could think of them as twin pillars.
Mm-hmm.
One helps us find the planets, the other helps us understand them once we've found them.
Nice analogy. Okay, so high level first. Both Kepler-725c and K2-18b, they're in that kind of super-Earth or maybe sub-Neptune category,
Cool.
right? Bigger than Earth, smaller than Neptune.
Correct. But that's almost where the similarities end in terms of the story. The big difference is how we found them and what we've learned since.
Right.
Kepler-725c is a very recent discovery, announced by a team led from the Yunnan observatories. And it highlights a really clever technique for finding planets around stars like our sun.
Okay, and K2-18b.
K2-18b has been around the block a bit more, study-wise. It's become famous for a completely different reason. It's one of our best shots so far at actually studying an exoplanet's atmosphere in detail.
Gotcha. And they're in different neighborhoods, too. Kepler-725c is way, way out there, like 2,472 light years.
That's the number, yeah.
A long way off.
Whereas K2-18b is, relatively speaking, practically next door at about 124 light years.
Much more accessible for follow-up, yeah. And
Right.
orbiting different stars, too.
Right. Kepler-725c is around a Sun-like star, a G9v. K2-18b orbits a red dwarf M3v class, cooler, smaller. And that star difference is pretty fundamental. It changes the habitable zone, potential tidal locking, radiation environment, lots of things.
Okay, let's dive into Kepler-725c first, then. Because that discovery method, transit timing variation, TTV, that sounds pretty cool.
It really is. TTV is fascinating because you're not actually seeing the planet you're discovering, at least not directly crossing its star.
So how does it work?
Well, you need a system where you already know about one transiting planet. In this
Yeah.
case, that was Kepler-725b. We could see its transits.
Okay.
If there's another planet in the system, even one you can't see, its gravity will pull on the known planet, Kepler-725b, just slightly.
Like a little gravitational nudge.
Exactly. And that nudge makes Kepler-725b arrive a tiny bit early for some transits and a tiny bit late for others, compared to a perfectly regular clockwork orbit.
Ah, I see. It messes with the timing.
Precisely.
Mm.
By measuring those small variations in the transit timing variations, scientists can work backwards. They can figure out the mass and the orbit of the unseen object that's doing the nudging.
And that unseen object was Kepler-725c. That is seriously clever. Detecting the invisible by its effect on the visible.
It is. And the sources highlight this is a big deal because it's the first super-Earth found using TTV specifically in the habitable zone of a sun-like star.
Sun-like star, yeah. That's
Yeah.
key. So what did this TTV method tell us about Kepler-725c itself?
Well, based purely on those gravitational wiggles, we get an estimated mass, about 10 times the mass of Earth.
10 Earth masses. So it could be rocky, it could be something else.
Could be a big rocky world, yeah, or maybe what we call a water world with a significant amount of water making up its bulk.
Right.
We also get its orbital period around 207.5 days.
Okay.
But here's the real kicker. The orbit is highly eccentric, about 0.44.
Whoa, 0.44. That's really stretched out, isn't it? Earth is like 0.01 Cs, almost nothing.
Exactly. Very elliptical, which means even though it orbits a sun-like star, its distance varies a lot. It swings into the habitable zone, then back out again.
So sometimes it's potentially just right, temperature-wise, and sometimes maybe not so much.
That's the implication. Big temperature swings, potentially.
Okay, so we've got mass, orbit, eccentricity. What are the big unknowns for Kepler-725c then?
The big one is radius. Because we don't see it transit from our perspective, we can't measure how big it is.
And without mass and radius.
We can't calculate density. So we don't really know its composition. Is it dense like rock or less dense, suggesting gas or lots of water? We just don't know for sure.
And no transit means no atmospheric studies using that method either, right?
Correct. Can't use transmission spectroscopy if it doesn't pass in front of the star.
So actual habitability is still very much an open question, that eccentric orbit alone.
Absolutely. It makes things complicated. You need detailed climate modeling, and even then, we're missing key data. But scientifically, it's hugely significant.
How so?
It proves KTV works for finding these kinds of planets, super-Earths, near the habitable zone, around sun-like stars even when they don't transit. These are planets that regular transit surveys might miss entirely.
Right, because they don't cross the star from our view. Or maybe they're just too far out on long orbits.
Exactly. So this opens the door. Future missions, like Plato or China's Earth 2.0, they can specifically look for these TTV signals. It gives us another tool in the toolbox to find potentially habitable worlds.
Okay, so Kepler-725c is a win for detection, finding the hard-to-find planets. Now let's switch to K2-18b. That one's more about characterization, right? Studying what we found.
Precisely. K2-18b has the advantage, as you said, of being much closer, 124 light years. That makes it a much easier target for our big telescopes.
It does transit its star, though.
Yes, it was originally found by the K2 mission using the transit method. We see it block out a tiny bit of its star's light.
Yeah.
But the really exciting stuff came from follow-up with Hubble, and especially.
JWST, the James Webb Space Telescope. That's where we got the atmosphere data.
That's the one. JWST has the power to analyze the starlight filtering through the planet's atmosphere during a transit. But first, let's look at the planet itself. Mass is around 8.6 to 9 Earth masses, similar ballpark to Kepler-725c. But for K2-18b, because it transits, we also have a radius measurement, roughly 2.4 to 2.7 times Earth's radius.
Ah, so mass and radius, that means density.
Exactly. Knowing both lets us calculate density, like knowing a box's weight and size tells you if it's full of feathers or rocks. K2-18b's density puts it in that sub-Neptune category.
Meaning
It's likely not just a big rock. It probably has a substantial envelope of gas, maybe hydrogen-rich, possibly surrounding a large water-ocean layer deep down.
a water world with a thick atmosphere.
That's one leading hypothesis, yeah. It orbits its red dwarf star quite closely, about a 33-day year, and its whole orbit is within that star's habitable zone.
But being close to a red dwarf often means tidal locking.
Very likely, yes.
Mhm.
One side perpetually facing the star, one side in perpetual darkness, like our moon with Earth.
Okay, so we've got this picture, maybe a warm, water-rich world, thick atmosphere, tidally locked, orbiting a dim red star. But the real buzz, the thing that got everyone excited, was what JWST found in that atmosphere.
Absolutely. Game-changer territory. JWST detected clear signs of water vapor, HEOO, also methane, CHRO, and carbon dioxide, QRO.
Okay, common enough molecules.
Common, yes, but finding them tells us a lot about the atmospheric chemistry, maybe clouds. But then there was the other one, the potential detection.
The one with the big asterisk next to it, dimethyl sulfide. DMS.
That's the one, DMS. Now this is where we have to be super careful. On Earth, DMS is overwhelmingly produced by life, specifically marine phytoplankton. It's considered a potential biosignature.
A sign of life. But you said potential detection.
Yes, and it's crucial to stress that. The signal is tentative. Needs more observation, more confirmation. There might be non-biological ways to make DMS, though current models suggest they're less likely in this environment, but the mere possibility, that's huge.
Wow, okay, and this connects to something called the Hyson hypothesis.
Yes, exactly. The Hyson idea, Hyson from hydrogen and ocean, suggests that planets like K2-18b, these worlds with thick hydrogen atmospheres over deep liquid water oceans, might actually be quite common.
More common than Earth-like planets.
Potentially. And maybe even better places for life to arise and thrive, offering vast liquid water environments protected beneath that atmosphere. It challenges the idea that we should only be looking for Earth 2.0.
That's mind-bending. Maybe the most common life in the universe isn't on rocky planets like ours, but in these giant ocean worlds.
It's a fascinating possibility, and K2-18d is the poster child for testing it. It lets scientists model these environments, figure out what biosignatures we should look for if life exists there. It really broadens our perspective on what habitable might mean.
Okay, so let's bring this all together then. Based on everything we've discussed from the sources, we have these two amazing planets, but they teach us different things.
Absolutely. Kepler-725c, its story is all about expanding our detection methods, finding planets in clever, indirect ways, especially those tricky ones, non-transiting, long orbits around sun-like stars.
Showing us new ways to find potential targets.
Right. Well, K2-18b is pushing the frontiers of characterization, showing us just how much we can learn about a planet's atmosphere hundreds of light years away.
Including maybe, just maybe, hunting for actual signs of biology.
Even in places that look nothing like Earth. You see the contrast in where we are with each. Kepler-725c, we know mass and orbit, basically.
Oh.
Indirectly inferred. K2-18b, we have mass, radius, density hints, detailed atmospheric gases, and that tantalizing DMS hint, further down the road of understanding.
But both are clearly top priorities for future study. Kepler-725c needs that radius measurement, somehow maybe direct imaging way down the line, or hoping its orbit changes slightly to allow a transit. K2-18b just needs more JWST time.
Definitely. More JWST observations are planned for K2-18b. To try and confirm the DMS, we'll look for other molecules, really pin down that atmospheric model.
And this comparison, it's important for you listening because finding Earth 2.0 or finding alien life, it's not just one discovery.
No, it requires both parts of the puzzle. We need the cleverness to find all sorts of planets out there, like the Kepler-725c discovery shows. And we need the power to study them in incredible detail, like we're doing with K2-18b, to search for those faint whispers of life.
So to sum it up, Kepler-725c opens new doors for finding planets, especially around stars like ours. K2-18b shows us how deeply we can probe the atmospheres of the planets we find, even hinting at biology in unexpected places.
They're perfect examples of the different complementary ways we're pushing forward in this grand search.
It really makes you think, though. The sources paint this picture of incredible planetary diversity. Worlds on crazy orbits around sun-like stars, these massive Hyson worlds around red dwarfs. It wasn't what we necessarily expected decades ago.
No, the universe is proving more varied, perhaps more creative, than we imagine.
So the final thought for you to ponder. What does this explosion in the known types of potentially habitable worlds tell us about where life might actually be hiding and what forms it might take? It might be stranger than we think.